Okay. So just 1 second. Here we go. Okay, this is the lecture 19. In this lecture, we kind of prepare some statements which we will need to prove some application later, about some application. It's a thing that from one point of view, the statements we deal with, actually there'll be two of them, do not seem quite interesting on their own, but important thing that they naturally appear in the application. The next several lectures, which will be dedicated to the Poisson-Nijenhuis structure, they explicitly use this statement, which is a good example of work with our cohomology theory. It shows that in case we do not deal with the diagonal operator, you will encounter some difficulties. If you remember, in previous lecture, we formulated some conjectures, and those conjectures were formulated for diagonal operators and with constant eigenvalues and with non-constant eigenvalues. If you recall, we do not formulate any conjectures considering, for example, differential and non-degenerate operator. This statement we deal today, which is called one cohomology lemma, is the reason we do not formulate those conjectures, because we see how complicated stuff there, and we will get we will see the problems we encounter, and from these problems we understand what kind of technology, what kind of machinery we need to overcome these problems. Okay. So let us recollect some facts. Okay. Same as before, the Lie derivative along L. L is an operator field, is a derivation of degree 1 of is a graded derivation of degree 1 of the complex of differential forms. The Lie derivative is defined as we moved to this Lie derivative through the Frohlicher-Nijenhuis bracket and through the graded bracket on the space of graded derivations of omega, but we can get this derivation using several axioms, right? What does it say? The axioms, I mean, those axioms, they naturally appear in different literature. Sometimes this second derivation on the space of omega is defined using this axiomatic approach. It is a good approach. It does not allow you to see the entire picture, but it allows you to see how this second derivation appears. So in recollecting the fact, we are in fact formulating this in a sense of axiomatic approach. So first of all, we assume that L along L, Lie derivative along L, is a linear operation. It means that it takes the sum of differential forms and the result is the sum of operations. And it means that if we multiply by a number, then we can get number out of the sign. The second thing is how we define this operation on functions. We define this operation on functions like this. We take the regular differential and we apply the dual operator, the dual which acts on the space of on cotangent bundle, not on the tangent bundle. The third is we establish the relation between our operation and the operation D. This relation is as follows, right? It means that the sum is 0, but okay, the sum is 0. And we assume that this operation is a derivation of degree 1, right? This is what it is written here in the fourth condition. Okay, so all the necessity of all this condition is quite obvious, because L is a derivation by definition. The second derivative, it's just the action of L of this Lie derivative along L on functions defined using the formulas we've discussed, because if you remember, the Lie derivative along L, it's a graded commutator of the interior derivative along L and D, and the interior derivative along L applied to the function yields us 0. So we get we need first to apply the derivative, the differential D, and we get the one form, and then we apply the inner derivative. It means the inserting L inside, which is again just L applying dual L to differential of f. This is just definition of the dual operator. The third comes from the Nijenhuis theorem. It was proved that the Lie derivatives, they do commute with differential D, and this is the necessary and sufficient condition for the differential, for the graded derivative to be represented as a Lie derivative along some vector value differential form. So it is again necessary. And the fourth is just by definition of the graded bracket, the insertion operator, the interior derivative, it has degree 0, and the D operator, it has the degree 1, so the graded bracket yields us the differential of degree 1. So this is what we get here. So those conditions are necessary. Now it's a good exercise to get to understand that those conditions are sufficient, that if we define the operation using these 4 conditions, then we get exactly the operation, the one we got from the graded derivation. So how do we do that? Well, if we look at the last condition and apply the squared, right, the squared, then we get the following. If we apply once, we get derivation like this. This is, we use the grade 1 derivation. Now we apply the second one, and we see if applied to the first one, we get this one squared. Then if applied to the second one in this formula, we see that because the Lie derivative along L, it increases the degree by 1, so we get negative 1 k plus 1, and we get this. And then we if applied to this, there is no extra. There's only has degree k, but it's first argument, so there's no change here. And I'm sorry, this is supposed to be wedge product here, not the sum. And here it is. So we get that those two vanish because k plus 1 and k, they have different signs. So we see that if we have a Lie derivative squared, then applying this argument, we see that if it is squared, and we know that it is squared, right, supposed to be 0, we see that it is enough to check that it is 0 on 1 forms, right, on 1 forms and functions, because those in the middle, they vanish, and we get that if we have a derivative like this, we need to check that the second derivative vanishes only for the basic derivative, because the entire algebra of of the differential form is generated by differential form of degree 1 and differential form of degree 0. But we have a condition 3. Which implies that if we take the Lie derivative, right, the Lie derivative on the function, then it automatically defines the Lie derivative on the differential of this function, right? So I'll take this here, I put function, then apply D, and I get this. This is the Lie derivative on the acting on the function. This means, actually, what it means. It means that my operation due to all these conditions holding, it is uniquely defined by its action on the functions, actually, because we know that all the differential forms, they're generated not only by 1 forms, but actually by exact 1 forms and functions. So each form can be written as a linear combination of basis vector forms, of basis 1 forms, which are exact, and multiplied by some functions. So that's what we're going to do. We see that all these conditions, they say that the Lie derivative, it is uniquely defined on by its action on the functions, right? So using this and this condition, right, we need to prove that it is squared is 0 follows from these conditions. It is 0 only on the functions, right? So on the functions. Well, if we apply this to a function, it's what we did in our previous lecture. We get the formula for the Nijenhuis torsion, and we get that the Lie derivative along L squared vanishes if and only if L is Nijenhuis. Because if it vanishes, if L is Nijenhuis, then it vanishes because of these conditions, and because this vanishes. And if this vanishes, we get that sufficient necessary condition is this, and Nijenhuis is obviously vanishes. So we see that this is a necessary and sufficient condition. The if this condition, the sufficiency of this condition is obvious, but the necessity is not so much. But because of these properties, we get that the corresponding Lie derivative along operator field is 0, being squared. So it defines the second cohomology theory, another cohomology theory. Okay, so the thing is, the other thing which is unexpected, is that we can multiply these two operations. Actually, we can d and multiply it by Lie derivative, and we get another operation which actually skips 1 degree, and it sends the forms of degree k to the forms of degree k plus 2. Well, this operation, it's not a derivation of degree 2, right? Because it does not respect the wedge product, because it's just a multiplication of two derivations. If we do the calculations, we'll see that the graded derivation condition here is supposed to be 2k. It means it's supposed to be plus here because it's degree 2. It does not hold for this multiplication if we replace this with a big D. So it means that it's not a graded derivation, right? But this operation is still very nice. It's still very nice because if we take the square of it, it's still 0, right? It follows from the fact that d squared is 0, and that Lie derivative along Nijenhuis operator squared is 0, because we have also this relation, right? So we multiply it. So we get this sort of differential forms with this sort of one more differentiation, d, big D, which again defines a good cohomology, right? But we do not dive into this because this cohomology is way more complicated. We'll see later on. But which is fun that it is, right? That it defines the cohomology. And it is, we can look only on the even on the forms of the even degree, right? And consider the omega 0, and we get the following formula. See, we apply this, and get that the condition that the formula is exact with respect to d. It means that df equals to 0. It is equivalent to the fact that f is a conservation law for L. We have discussed the conservation laws, and we discussed that they naturally appear when you deal with a system of partial differential equations. They are the natural density of the conservation quantities. If you integrate the conservation law, the density of the conservation law, if you integrate it, then you'll get something, if it's not infinity, which does not change over time. So thus this operator, it has some important information. The next cohomology lemma, it's not a cohomology lemma I'm talking about. This is the simple discussion of the conservation law. If you remember, we discussed the conservation laws for the Jordan block, and we had a algebraic operation. If Jordan block with a constant entries, with a constant eigenvalue, maximal size, we took the coordinates in which this operator is a Jordan block, and we showed that you have some sort of algebraic trick which allows you to obtain all the conservation laws for this Jordan block. It was quite simple. It used you just take this Jordan block, take its power. If you remember, you multiply them by variables, then you substitute into some function, and you get the coefficients of the decomposition of this function. They are what you need. In diagonal case, this is the case we deal with. Today we talk about differential and non-degenerate geometry. It means we remember that differential and non-degenerate operators have a structure that in the neighborhood of the point of general position, they have the following form, right? They're diagonal, and the eigenvalues, they are differential and non-degenerate. We say that the conservation law is like this. See, it is defined by n functions of single variable. See, again, that if you recall that for the same operator, the cohomology which relates to the Lie derivative along L, we discussed it. The conjecture is that all the cohomology groups vanish, right? And here we have that the cohomology group is somewhat defined by n functions of single variable. So how do we do that? We just calculate, which is a good exercise, right? So what, this is supposed to be f here, I'm sorry, it's typo. So what do? You take the differential, it's like this. You assume that you have an arbitrary function, then you have a differential, then you apply L, the dual operator. It is actually transposed, but in our case it is the same. It's because it's diagonal. So you get like this. You get a differential form with a coefficient coefficients that look like this. That's a partial partial derivative of f multiplied by the corresponding coordinate which you use to derive, right? And then you apply d. Okay, how do you apply the differential to the one form? You differentiate each one, and you take the partial derivative, and you take out the d, right? dx I, for example. What is important then, when you differentiate this formula in all the x's except x1, x1 can be taken out of the differentiation, which is good. And you do not differentiate in x1, because if you differentiate in x1, you get the x1, it's in which product is 0, right? So you take the derivatives of this in other variables, and you have some here the term which you differentiate in the x1. So the formula, the final formula you get is like this, see? Because you take the xi and differentiate in j, they are not equal. Then you take xi and you take xj. So this is the formula. This is the formula for this for basically this operator d acting on a function, right? So if we look at the second derivatives, it's supposed to be 0, right? This f, again, this f is missing. So it's supposed to be 0, and see that all the pairwise different derivatives, they vanish, because this coefficient is not 0 almost everywhere. Which implies that the function is like this. It means that it consists of just sum of functions of single variable, n functions of single variable. This is important. We see that the conservation laws, they are generated by n functions of a single variable, right? Okay. Okay. Now, next. So it's all, everything is analytic category. This is like the most, the theorem. This is that the cohomology equation we want to solve, right? This is rather standard cohomology equation. If we talk about regular cohomology, then it's supposed to be df equals to one form, right? And we all know that Poincaré lemma, it states that if we differentiate this function using that the necessary and sufficient condition for this equation to have a solution in local coordinates with respect to f, right, is that the right-hand side is a closed form. It means that you take differential d of the right-hand side, it's supposed to be 0. That's simple, as simple as that. Well, now we take a look at our this cohomology equation, right? This cohomology equation, it involves not the d small, but big D operator, right? So it skips 1, so it's degree 2, and it means that we have a cohomology equation of the same sort, which df equals to omega, which is omega is the form of degree 2, right? And the natural question is, what is the condition for this omega to vanish? Okay, it turns out, if we look at this this formula, because of the condition 3, because we can change the application of the sign, we see that the necessary, right, the necessary condition for this equation to hold is that omega is closed with respect to d small, right? If I apply d here, I can change with the different, with taking minus, and this will be d squared to f, and it will be 0. So it's closed with respect to d, right? This is, and if I use L along L the second time, then it's squared and it's supposed to be 0. And I see this. These two conditions are obviously necessary because we know how those two operations, the lead derivative along L and the differential D, how we can change them with changing sign, right? So these conditions are necessary. Okay, it turns out that these necessary conditions, they are sufficient, which is quite interesting, right? It says that those in terms of cohomology, it says that if we take the exact form, it means that if we take closed forms with respect to D and closed forms with respect to L and intersect them, right? An intersection of the differential form is a very bad idea because, well, it's an infinite dimensional space. You can take the intersection and you get the forms which may or may not be of good form or whatever, but it says that all these forms, the intersection, right, it consists of the image of operator D, right? So this operator, at least on one forms, on 0 forms, it acts really nicely. You take, you intersect the closed forms for both differentials, and you get, and the D is exactly the image. Okay. So those conditions are necessary and sufficient, right? We see that those conditions, they're kind of stronger than if just we apply D second time to both sides, right? Because if we apply D to this, we get the form of the 4th degree. But here we have two conditions on the form of the 3rd degree. Okay, so this condition is stronger, but this again, the statement of this theorem, it naturally appears in the application. You will get to this in the next lecture, but this geometric, this is a really nice geometric question. So what is what we're gonna do? We're gonna solve it, and we're gonna solve it for differentially non-degenerate operator. The solution, the theorem, the proof consists of 2 big parts. One part is rather simple and straightforward. We do not start because, as you recall, we did not calculate any cohomology for the differential non-degenerate operator because it's kind of very complicated, and even in canonical coordinates. So, but we calculated the cohomology, and we did some calculations with the operator which is diagonal, which is the differential non-degenerate operator in the point of general position. So that's what we're going to do. First, we're going to look at the point of general position, right? And there, in the point of general position, we get that the operator is diagonal and the x is on the diagonal. And in this formulation, we're gonna do some calculation. Okay, so if it is diagonal and both conditions hold, then we have that one form is closed, right? It is closed with respect to D. Then I can write the lead derivative of L as like this. This is the graded bracket of differential D and inner differential of degree 0, the insertion of L. So I write it, and I see that because omega is closed with respect to D, then I have the following condition, right? So it just vanishes this part, and we get this. So in these terms, I can write that I can rewrite this condition as follows: that the form omega and form AL omega, both forms are degree of 2, right? And they're both closed. So this is the second condition. So the second condition, that this form is closed. Okay, so how do this inner derivative of degree 0 works on this omega? It works rather simple. It's like this, and I apply the formula which I proved in some previous lecture about differential about the differential forms and Nijenhuis brackets. Okay, so the first I rewrite these conditions in the following sense, and then I write the omega in general form. It's in general form like this. Okay. Okay. Then, if I look at this in these coordinates, the operator L I substituted here, it means that if I'll take the basis vector fields, that these elements, they are the result of application of omega to basis vector fields partial E, partial G. So, and both partial E and partial G, they are eigenvalues with corresponding coordinate, right? So if I'll take this partial E, partial G, right, to this, and because of this formula, I will get xi here and xj here, and I get exactly this. So I have that one form is has entries omega, and the other has entries like this. The equation that this formula holds, because we've already calculated here the formula for the second, for the application of D, of large D to F, we get that the formula can be written like this. This is the cohomology equation for the diagonal operator. It's not scary. It's really nice. We can see that, well, we have a operator, we have second derivatives. So we resolve this with respect to the second derivatives, right? So we have an equation, and we kind of resolve it. We write it like this. This is a regular cohomology Pde, right? The right-hand side. We do not need analyticity here. We'll see that analyticity appears later, but here we have a regular cohomology Pde. It means that we have two forms, and we have on the right-hand side we have a two form, and on the left-hand side we have second derivatives, and we ask ourselves when this solution can be, when this equation can be solved with respect to F. Right, and we've discussed this regular cohomology equation. It means that it can be resolved with respect to F if the right-hand side satisfies the compatibility condition, right? The compatibility condition. Okay, what are the compatibility conditions? They're as follows, right? It means that if, well, basically, if you have this partial derivative of in x, in I and j, and you differentiate along k, and same do with it interchanging the coordinates, you get the same, because the partial derivatives, they must all be the same, the partial derivatives of the third order, right? So this is the condition. This is the condition I get. It can be rewritten as follows. We see that these conditions, they are nice because xi and xj, they are like constant when we differentiate along xk, so we can take them out and we get the formulas like this, right? So we just rewritten these formulas like this. Now, so these are the conditions we want to prove, right? We want to prove that the omega satisfies this collection of conditions, because these conditions are necessary and sufficient for this equation to have a solution in F, right? Okay, But what do we have? We have that omega is closed with respect to D and closed with respect to L, which means that this formula is closed, or which means that this is closed. Okay, so what is the closure condition for the two form? It is like this, right? It is just you take the sum of indices there in the correct order, you change them in a cycle, right? And the sum is 0. And the same goes for the two form after we use the inner derivative in L, right? So after we use the inner derivative in L, we get that this formula holds, but we see that again, taking the component of the differential two forms, differential two form, it is multiplied by xi xj, right? And when we take the derivative, it takes out, so I get the following form. Okay, so I get this. This is a system I have. It looks quite nice because I have three components here. They're both, and we have two equations, which seems that it is the number of equations coincide. And I go straight ahead. I divide this equation by the first component, and I subtract this equation from this, right? And after the subtracting, I get the following formula. See, it goes like this. If I bring those two to the common denominator, right, I multiply it by xi plus xj and subtract it, the xj vanishes. So I get xi minus xk, and I get xk minus xj right here in this formula. And it is 0. I multiplied by xi plus xj. See, because all those formulas, they hold almost everywhere. Right, if both coordinates they vanish at least they vanish in some points, but we assume that they do not, right? So this is an extra condition of the general position, right? So and I can multiply it by this and divide by the power of this, by the product of this. So I get that this is supposed to be divided by xk minus xj, and this is divided by xi minus xk. This is this. I'm sorry. This is exactly this formula. See, so I can do the same for the second and the third, and I get that this condition holds. So I see I did it for the first, and I prove that this part of the equation. If I'll take for the third, for example, I will prove this part of the equation, and I'll get that these conditions hold. So these conditions, they algebraically simply follow from these two conditions. Very simple, straightforward calculations. So we see that those conditions hold, right? And this means that we proved that the statement of the theorem holds, right? So if we take the derivative in D, and we take the derivative in L, right, in diagonal, then this statement is proved. It's an interesting statement on its own for the diagonal operator of the form we have discussed. It has a quite long history. It's appeared in the work by Gelfand and Zakharevich on the in the question of Hamiltonian geometry, in the Hamiltonian geometry. And basically what we have discussed here was used to prove that a specific kind of Hamiltonian structure you will meet in the later lectures. It has a very nice normal form in local coordinates. And this proof, what we did, we generalized this proof for the differentially non-degenerate operator. It required different mechanics, because original proof did not use any cohomology theory or any calculations like this. So it required some work, but it's still a very nice result. Okay, so just a second. Okay. Now we assume that we have a coordinates in which operator is in the form like this. As you recall, the basic facts about the differential and non-degenerate operators are the operators. Again, with the coefficients of them, with the coefficients of characteristic polynomial being functionally independent. It means that we can take these coefficients to be the coordinates, right? It turns out that the if operator is Nijenhuis, then it leads to a very specific normal form. It's the form like this, because the coefficients of the characteristic polynomial, they satisfy the set of the conditions. These conditions follow from the vanishing of Nijenhuis torsion, and for differential and non-degenerate operators, they are actually equivalent, right, to the Nijenhuis condition. We get this collection of the conditions which force the operator to look like this. If you remember, we discussed that we in fact have two. This is exactly the companion form. If you remember, this is an important fact for GL regular operators, that they have companion form, and differential non-degenerate operator is GL regular operator, and we always assume that it is GL regular. We have proved actually this lemma that for Nijenhuis operator it's supposed to be GL regular. So there is no differentially non-degenerate operator which is not GL regular. Okay, so this is the normal form of this operator. X1, X2, etc. They are just coefficients of the characteristic polynomial. We name them the same. It may or may not lead to some confusion, but it's okay. And we dive into the calculations. Okay, we see that the calculations are really bad. They're way worse than they were before. Remember that this is the calculation for the diagonal operator. It yielded us the following. See, look at this. Look at this formula. See, this when an operator was diagonal, it was a very simple, very nice formula. And here we have a huge complicated formula, but what we do, okay, that's what we do. We take the differential of f, it's a differential, then we apply the operator L. It is supposed to be, you should take the dual operator. The dual operator is actually, can be understood as follows. You can multiply the row from the other side, or you can just transpose operator. In both, if we take a row of partial derivatives and multiply it, the operator from the right hand side, we get that first you multiply this column by this row and you get the following sum, right? This is the sum, and this is the sum which is the first component of the one form you get after you apply the operator, right? So the first component is all the derivations along this column. The next, you take this row and you multiply it by these columns, and you get that the second column yields you the first derivative, the third column yields you the second derivative, and so on and so forth. And the last derivative, the last column, it yields you the derivative with number n minus 1. This is exactly what we get. So here we get the derivatives, and the number is one lower than the basis one differential forms. Okay, this is just to apply the L star very carefully. Okay, so to avoid confusion, now we apply the differential, right? So we need to differentiate this one form. Okay, so what do we do? First of all, we get that we need to split the sum, the result sum into. See, we obviously have some complications when our wedge product contains dx1. So we assume first that it does not contain dx1, so it contains only dx something and something. So I'll take I and j, and they're both larger than 1. So I see that the formula is quite nice. So I take this derivative, it will be the second derivative, and I see that this I j minus 1 comes from the differential of the coefficient for j, and I minus 1 xj comes from the differentiation of coefficient in dx, and because I switch them, right here I get negative sign. So I get the following formula. See, it's quite nice. So I kind of change the The second derivatives. Okay, what about dx1? Okay, so first of all, I have all these terms. If I take the second derivative in dx1, and that's what yields me this coefficient. See, so I take this dx1. Then I need to differentiate this in some other, not 1, but in some j. J is greater than 1. So if I differentiate it in j because of the x, I'll get that I get the first derivative, right, with a negative sign, because I'll get the xj and I need to switch it. So I get this with a negative signs of xj, and I get the second derivative. There is a summation here in alpha starting with alpha equals 1. Here, summation starts with alpha equals 1. Okay, so this is the result. I see. So you see that we have complicated formula for the terms that contain dx1 and dxj, and we have a rather nice formula which has which has terms which contain I and j. Okay. So again, we get the following system of PDE. What is this system? This is the system we want to solve. Okay. This system again looks very, very bad. Why? Because we have an omega on the right hand side, if you remember, right? This is what we do. We take this and we have omega on the right hand side, and it looks like this. This here we have a terms with indices 1j, and j changes from 2 to n. And we have ij with the I is in both ij is not the 1, great like this. So we have the formula like this. Again, in diagonal case, this formula was rather simple. It had the following form. This is the formula we had in diagonal case. Okay. And but what we actually want to try to do is we want to resolve this system. It looks horrifying, right? It is written here because it does, right? There are a lot of equations here. Those equations, they complicated, and they involve different partial derivatives. They kind of mix them up because you have ij here and you have ij here. So what we're gonna do is we're gonna look at the property of this equation in general. Okay, in general, it turns out that this equation is not so bad. Well, the formulas are horrifying, yes, but what we're gonna do, the first step we're gonna do, it's a standard analytical step. If you want to understand whether your system of PDEs has or does not have any solution, what you need to do is you need to look at the resolving this system with respect to the derivatives, right? To the higher derivatives. Okay, if you have, if you remember the statement of Cauchy-Kovalevskaya theorem, it says that the system can be solved if you have the largest derivative, like of order k, and you express this derivative as a function of derivatives of smaller degree and maybe the derivatives of the same degree, but this degree, it contains some coordinates which we assume independent. We'll understand it later. So this is what we're going to do. We're going to try and ask ourselves, can we resolve this system of equations, which is algebraic now, right? With respect to the second derivatives. Again, in diagonal form, this was very easy. This was our this is how it looked resolved. It was a system of second order partial differential equations, but the right hand side, it depended only on x, so it wasn't actually the system of PDEs. It was, you could have just solved it by integrating it, right? Okay, and we got that if we integrate this system, this system is it turned out to be compatible, right? And it means that for any initial condition, we have a solution. What does it mean in this case, in this diagonal case? Well, it means that when I search for a function f, then I can pick the following. I can say, well, again, go back. See, here it is. In this case, I have only I is not equal to j, right? So basically, I say, well, if I look at this system, if I look at this system is linear, and it is defined up to the addition of some other function. I call it f, I don't know, star, which is closed in the following sense, right? Which is a conservation law, right? So I say, well, okay, solving this equation, I can do the following. I can pick a single function of one variable, which will be, this is like the degree of freedom, and I also will need a value of a function at the coordinate origin, right? But this is the value of the function at the coordinate origin. It is not important, right? So basically, I see that in this case, the system, it looks absolutely differently from the ones we have just discussed, right? But again, the solution of the system, it depends on n functions of single variable, right? So because again, it's linear, if we subtract it and we get that it is defined up to the addition of a conservation law, and conservation law, we started with this lemma, it is defined in diagonal form with respect, it is defined by choosing these functions of one variable. Okay, so this is it. So this is the property of the system, right? Such systems, they call the systems in involution. But I think you have discussed it. So this system does not look anything close to what we've discussed earlier. But again, do we want to resolve it with respect to the second derivatives, right? The first thing is if I'll take j equals to n, right? If I take j equals to n, I see that this derivation from this first equation can be resolved as like this. I'll take this, I'll take on the right hand side. This is the first unpleasant surprise. I see that my second derivation, it depends not only first derivations, but it depends on the second derivations, one of which is derivation in n, like in last variable. See, it turns out that this is the property of the system. We cannot get rid of this. We cannot just make a nice resolution as we did before. That is, we have equations of all the second derivatives, they depend on only just on the x on the right hand side. This is not what's going to happen, right? But we still have the derivation here. The second derivation is resolved with respect to first derivatives. First derivatives, which is the f xn, and the second derivatives, which one of the nj. So that's what I write symbolically like this. The second derivative, it is resolved just simply by taking this and taking to the other side. Okay. Now I'll try and resolve for the j, which is n minus 1. Okay, I substitute n minus 1 in here, and I get the following formula, right? I get, and I take to the right hand side, I get the following formula. Here I split it from this sum, right? I took alpha equals to 1 separately, and I took all the other sum, and again, it is here. So I see. So I get, this is the function of x, then I have the first derivative. Okay, it's not scary. I have the second derivative. Look, this is exactly the derivative we have discussed earlier. This is the derivative we got that this formula holds, right? So I can take this and substitute it here, and I'll look at this last derivative. I see Here it's not anything we've encountered before. It is alpha 2, 3, 4, etc., etc. Okay, but what I can do, I can look at the second equation. This is the second equation. This is the second equation, right? And I apply the equation I get. Look, for j equals n minus 1 and alpha, I get the following formula. Look, I get the following formula, right? And this depends on x. So what I can do, I forgot here, there's a typo here. It's supposed to be omega alpha n times x alpha. X should be either here or it's multiplied here. Each omega is multiplied by its own x, so the formula is it's more complicated. It's not just the sum; it is sum multiplied by the coordinates. Okay, so I'll take I equals alpha, and I take j equals n, and I get the following formula. This is the formula from the second collection of equations. See, this is the first collection of equations. We have n-1 equation and all the others. So I get this. So applying this symmetry here, like so, I take this formula, apply this symmetry, and I get again that the right-hand side of this second derivative, it depends on x. All the x is x1, etc., xn. It depends on first derivatives. And it depends on the derivatives of f in xn, and you take the second derivative, one of which is derivative on xn, right? So I get that for n minus 2, the same similar formula holds, right? Because I obtained it because I obtained this formula for the n, right? And now I obtained it for n minus 1. This is j. Okay. So this is what I get. I can do the same procedure again and again. So every time it will be, the formula will be similar to this. I will get n minus, I don't know, s minus s. It will be 1 n minus s. Then the partial derivative n minus s. This is, I rewrite this. And I'll take, and I have to split some sum from the sum, and it will be dx1 n minus 1, then dx2 n minus s, dx1 n minus s, dx2 n minus s, dx3 n minus s, etc. For dx1 dxn minus s, this is exactly the previous. For dx2 xn minus s, I'll apply this formula and I get dx1 dxn minus s plus 1, and I get again the previous case, and at the same time I get the addition of this multiplied by x1, etc., etc., etc. Same thing goes here, and when I get this n minus s, and I get alpha starting with the s, right? So alpha here starts with 2, here because 2, and for n minus s here alpha starts with s. And I get that inside, applying this trick several times, I get dxn here. So again, because of all the previous results, I get that my derivative of n minus s, which I denoted j here, it is expressed like this. Okay, so in I, j here changes from 1 to n minus 1, and here it is supposed to be, I'm sorry, this is supposed to be a derivative in n. That's not the same j is here. That's different j. It's supposed to be I here, and I changes from 1 to n. It's supposed to be a typo. It's not j. Here it's not j. It's I, and it's I here. And it changes from 1 to n. So I get the following formulas. So that's what I did. I started with the expression of the second derivatives, which contain partial x1, right? And I expressed them in the following form. I didn't express them as x's, but I expressed them like this. I expressed them as a function of first derivatives and the derivatives containing xn. Okay, looks nice. Arguably looks nice. We could have expected better, but it turns out that the system is complicated. I mean, it's we do need some calculation and need some ideas. So Now we look at the second system, right? We look at the second system, and that's what we do. If we look at the second system and take I, j minus 1 for I and j greater than 1, then we can apply this second system. See, you kind of lower this index, you increase this index, and you have to add this omega, because if you take this. And if that's what I'm gonna do. I'm gonna take I and I'm gonna try and get to the 1, right? To the I equals 1. Or if it's not possible, then at some point I will stop at n, right? So this is the case when I assume that it is possible, right? That it's I plus j minus 1 minus 2 is lower than n. So that's what I do. So I take this second derivatives, then I apply this trick several times, see first this, then apply a trick to this, and I get this formula, and I get the following formula, right? And I have already proved that this is a function, the one I need, and I add some function in x. So it will be some function this and like this. So it is holds for this. If I plus j minus 1 is greater than greater or equal than n, then at some point I get to the point where there's some derivative here and have a derivative in n, and again I have a sum of functions in x's, right? Which is again means that the mixed derivative, it goes like this. So again, we started with this system, and we looked at this system as a system of algebraic equations on first and second derivatives, and we expressed the second derivatives in terms of first derivatives and x. So we get the following formula. This is the general formula. What does it mean? It means that this formula I did not calculate the functions f, I, j precisely, right? I just introduced the procedure which states that this system can be resolved like this. Note that, well, the important thing here is when we do all these calculations, we do not get them. We do not get maybe the entire system. So we kind of study the subsystem, the fact that this new system, it is equivalent to the old one. It is an algebraic question, right? Which is complicated because, well, I can show you the source of complication. One source of complication, for example. Recall that we first did this trick, right? And it is a nice trick. And everything is fine here. We just took the second equation, brought it on the right hand side, and everything's fine. But in the next step, when dealing with the n minus 1, we need to substitute this formula here, and this is multiplied by x1. And in this case, we had this thing multiplied by x, and after we multiplied it by x1, we get that now we have this multiplied by x and this multiplied by x in the second power, right? And then we again taking n minus 3, right? We get 2n minus 3, which gives us 1n minus 1. We get multiplied by function, and then we get dxn, dx1, dxn minus 2 multiplied by some x. So I will get the x in the third power, right? So in the beginning here, the formula was simple. The coefficients were either constant, those coefficients constant, or linear in x. But each time I'll apply this formula. I try to express the second derivatives. I will get the more complicated formula, even in terms of powers of x's, right? They increase each time. So when I get to the j equals to, let's say 2, right? So dx1, right? I will get the power n minus 1, right? This will be a huge formula. So when I write this, I did not calculate the formula, but this is the general property of this system. It means that this system if we take subsystem, right, that we take a huge system and we take some of the derivatives and we say that they expressed in terms of other derivatives, right? Well, this is the subsystem we're going to study. We'll see that this is exactly what we need, right? So took a look at this system now. This is like the source of our study, and it does not necessarily mean do not need the exact formulas for this these functions. We'll see that the only thing we need is like this. Okay, so studying the companion form, we got to the point that we needed to solve a system of partial differential equations. So what we did, we calculated the compatibility conditions of these partial differential equations. Okay, if you remember all those equations, they were on a vector function. Here the equations is different. We are searching for single function, right? But the system we're dealing with is a system of the second order. We deal with the second derivatives. It turns out that in this case, exactly the case I'm discussing, the initial conditions are different. The initial conditions are different in a sense that the initial conditions, they go like this. Again, I have n functions, initial conditions, and those functions are, I'll take f, and we assume that we work in the coordinate origin, and I get that if I'll take all the x's except the last one is 0, then this function and all the derivatives except the derivatives in n, right? The derivatives in n, they are the initial condition. Okay, right. So you see that we have an initial condition in the following form. The interesting thing that initial condition in the sense of number of functions is the same as we had before. This system, again, looks very different but the number of initial conditions is the same. N functions of single variable. Here we get that, again, we have n functions of single variable. Okay. This is an important observation. This is the property of systems in involution, and this is the thing which you check when you prove that the companion form exists. So, okay. Now, what we're gonna do is we're gonna check the compatibility condition. The compatibility conditions, again, they come from the general theory of partial differential equations. They look like this. They look actually quite similar to the compatibility conditions we have discussed earlier, right? And this is important thing. Or the only difference is that I, j, and k they vary in different coordinates, right? So it means that they cannot be n. They all must be 1, etc., n minus 1. Okay. So first of all, we will need at least some sort of general formula for Fij. Well, if you remember the process we used to establish, it is usually in the second part nothing changes. You just add the function of x, and in this case you multiply by x, right? And again, this formula, it is linear in the second derivative, it is linear in the first derivative, and you have an addition. It's not homogeneous, right? Because you add the function of x. So in general, we get the following formula, right? So you take f and you express it in terms of partial derivative which contains n. We take you express it in terms of first partial derivatives, and you have some term which contains x, and it does not contain any derivatives. Okay, this is the formulas for the PDEs we're gonna solve. Okay, now let us calculate at least one of these derivatives. Okay, we go like this. We apply to this, and this, the Leibniz rule. We get this, and we apply it to this derivative. Then we apply it to the first component and apply it to the second component, and like this. For when you calculate the compatibility condition, what you need to do is, well, actually, see, I took k and applied it to this, and I got the third power, and I got k, s, n, but I took n out, right? So I got, I written this component is like this. This is f, s, k formula for s, k. And here it is formula for s, k, right? So that's what I do. I substitute it. So I get this first term. It is okay. It contains only s and n. Then I'll take this term. This is just f, s, k written, expanded, right? And then I'll take this. I do not change anything here, and I'll substitute same sk here. See, it is like this. Okay, so now I open all the brackets and I get the following formulas. I get this formula for third derivative, right? You see that this third derivative, it is if in fact the first derivative, and it is the second derivative in n, all right? Okay, so then I get the second derivative, right? I get the second derivative, and I have the first derivative, and I have the term which contains them only x's, on function in x. So I see that this formula is very, very complicated, but what is important thing to remember? If you recall, and we'll get to this later, Nijenhuis torsion, when we were calculating the compatibility condition for vector valued functions, we had a problem there. Not a problem, but we have a specific, we had a specific property. We took quasi-linear equations, we took the compatibility condition, and the compatibility condition was actually a tensorial condition. You had a tensor which is supposed to vanish. And if you recall, that tensor was exactly the Nijenhuis torsion, not the entire torsion, but the symmetric part of it, right? So we had a quasi-linear system, and the vanishing was supposed, and those compatibility condition was supposed to be like this. The symmetric part of this tensor vanishes. And what we did is we proved that this symmetric part vanishes for compatibility conditions for Nijenhuis torsion, and thus we exactly obtained the formula for the first companion form and the second companion form. In case of second companion form, we use different matrices. Not in first companion form, we calculated the compatibility condition for the powers of L, and for the second, we calculated the compatibility condition for the matrices we called M. They were some linear combinations of L, or powers of L with some coefficients. Okay, but in general, that was a tensor field. But what do we get here, right? What is the compatibility condition in case we deal with a function of single variable? Of course, the compatibility condition is a collection of functions. They are not tensorial, right? When you change coordinates, those functions, they do not vanish. So how do I obtain these functions? Well, I'll take this thing, then I change the coordinates, and I subtract one from another. And I get the coefficients in front of partial derivatives of f, right? This coefficient, this coefficient, this coefficient, and this coefficient, right? And all those coefficients, they must vanish, and they vanish identically. And those ij, those are not real indices in the sense of tensorial thing, right? So you get you get functions which contain from this formula, they contain the components of A, they contain the components of B, they contain the components of C. They also contain the partial derivatives of components A, partial derivatives of components B, and partial derivatives of component C in all the coordinates. So when I write this formula, I get the following formula. The alpha is a collection of indices, which is quite large because you need to take all these equations, and you also need to consider 1, 2, 3, 4 for each. So you have a quite large system, Okay, this system is huge and terrible, and we cannot, in any sense, try to calculate it. See, because the compatibility condition, just the compatibility condition, it looks scary and huge. And to calculate those coefficients, we need to apply these formulas, this process, and we get, at some point, we get the polynomials of higher degree and stuff like that, and it's very, very complicated. Okay, so what do? We use a trick, which is differential geometry. As I said before, we deal with the functions. Functions, the good thing about functions, they stay the same in every coordinate system. The formula for function changes, but the function stays the same. So if function is 0 at some point, then it is 0 no matter what you do. You change the coordinates, it is still 0. Okay, now I say, well, okay, if I change my coordinates, what happens? Well, look at the point of general position. You can change coordinates there, and instead of operator L, you get a diagonal operator, right? You get a diagonal operator, and you get that the compatibility conditions, that the solution of your system, it is actually a set of compatibility conditions, right? And these compatibility conditions, they do vanish, because we have shown, right, that for every initial condition, you can take a function, and you can take n functions of one variable and construct the solution, right? And this means that this solution coincides with any other solution with the same initial condition in analytic category, right? So I constructed all the possible solutions locally in a neighborhood of a regular point, right? And I did it using this rather simple formulas. That's what I did. I constructed all the solution in the neighborhood of this point, which means that if I constructed all the solutions in the neighborhood of this point, then those functions I denoted C, they must identically vanish, because they present obstruction, right, to the construction of the system. You have a solution for each initial condition. You have a solution if and only if this thing identically vanish. So almost everywhere this function identically vanish, and thus they vanish everywhere. So see, so the proof of this property of operator D big, yeah, it included two parts. First, we calculated in regular points, and it was really rather simple. And then what we did, we calculated not in regular points, but we calculated them in general. But we have shown that the corresponding system yields you compatibility conditions, and those compatibility conditions, they live on the entire neighborhood. They almost everywhere vanish. See, so we use the compatibility condition, which is a part from the theory of partial differential equation, and we use the real nice form of the operator in regular points, which is a part of differential geometry. So in general, it seems that this strategy might be fruitful. You can try and attack this problem in general. So we have this simple conjecture, right? It is a simple conjecture. We say that the following condition holds for diagonal operators, right? It's more of an exercise, actually, but we say that, well, the simple part of our proof, the simple part when we do with diagonal, it actually holds all the time. We do not know if the complicated part holds all the time. So if we, instead of this diagonal operator, we take a differential non-degenerate operator, we don't know what happens there, because the compatibility conditions, they become way worse. Or maybe not. Maybe they still become tractable. You can still maybe apply this technology, because, well, for a system of PDEs, the technology does not change depending on how many equations you have, or how high the order of your equations. The compatibility condition will still be the same. But it's still very interesting conjecture. Well, it seems that you can definitely try and solve it for k equals 1, right? Taking one form and taking this differential, you will get 3 forms. You get 3 form, which seems complicated, but not terribly complicated, right? So that's it. Okay. And you will use this theorem we have proved in the next lecture. Okay. In the end, I wanted to remind you of Nijenhuis torsion and kind of finish up the talk, because in the end I realized that we didn't discuss this topic, which is sad, because it's a really nice tensorial property. So if you remember, Nijenhuis torsion, we denote it like this. So imagine that we have a system which looks like this. This is a system on functions u, which depends on x, which depends on t, tau, x, and y. We all discussed the systems which depend on many, let's say, many time variables, but the space variable was always the one, x. And when we talk about companion form, x was the last xn. We see that we have some sort of very special coordinate here. But sometimes you can have two special variables, two space variables, and more space variables. So you get a system like this with two space variables, x and y. So the question is, what is the compatibility condition? Again, the compatibility condition is calculated straight ahead. We differentiate this in t and this in tau, and we open the brackets. We differentiate this here in this formula. We used that the differential in x and differential in y and differential in t and differential in tau, they can be interchanged. So dt of u and y, in partial y, I take y out and I get u in t and apply this. So I get this. And I see that the conditions are quite similar to the ones we've encountered before, but with a slight difference. Look, here condition is the same. Those operators L and K, they must commute. But look at this condition. In case of one space variable, the compatibility condition, it had here x and x. So you took this tensor, which is Nijenhuis torsion, as we remember, and substituted two same vectors. And you assume that this thing vanishes. Substituting two same vectors, it means that the symmetric part of the tensor vanishes. But if you have two different derivations in x and in y, then you get two different vectors, which means that the entire tensor vanishes, right? So that is the difference. If you have one space variable, you have the condition for your system is vanishing of symmetric part of Nijenhuis torsion. If you have two space variables, then the condition is vanishing of the entire tensor. And this leads to the following lemma. It goes like this. Well, assume that we have a Nijenhuis operator and we took different powers, let's say L in power k, this is what it means, S in power S, it means again power, and ask whether the Nijenhuis torsion of these two operator vanishes. Well, I just tried this Nijenhuis torsion, and I recall that the vanishing of Nijenhuis torsion implies this identity, right? For every operator, for every vector for psi, this thing holds. We see that these formulas, they can be rewritten in terms of derivatives in psi or derivatives in eta. It depends on which one we like the most. But the important thing is that if we look, for example, into this, right? And we take the derivatives of, we take this and we take derivatives in this, and it means that I'll take the lead derivative along this vector field of L in power of s, and I'll take the Lie derivative of eta, and ls is taken out. And I see that if I'll replace this with the power of k, for example, here, right, that means that I can, if I'll take L in the power of k psi and substitute it here, then I take L one by one. So see, this means that if I'll have Lk here, then this is supposed to be Lk plus one here, right? I'm sorry, Lk, and I get Lk here, right? So it means, and remembering the Leibniz rule, we get exactly that this tensor vanishes. You have actually proved this lemma when Alexey Viktorovich was proving the companion form. So this is like the idea of this proof is to recall, for you to recall that original proof. But look, if you consider this, these properties, you get 0, and you get that the Froelich-Nijenhuis torsion vanishes, which means that those systems they're compatible, right? So they do have a solution. They do have a solution if you take different x and different y. And how do you apply this? We get the following theorem. This actually this theorem, to prove it, it's a good exercise, because what is the theorem? Let's take Nijenhuis operator in dimension 2n and assume that the algebraic, in algebraic sense, in one point at the coordinate origin, L is the sum of two Jordan blocks of dimension n. It's the case when you have a maximal Jordan block size, right? But not the maximal in a sense that it's 2n, but 2 of dimension n. And then you assume, in addition, the regularity condition. It's quite interesting. You assume that its characteristic polynomial is an exact square of some polynomial with a smooth functions, right? So it can be decomposed like this, with a1, an, etc. smooth functions. Then it turns out there exist the coordinates in which you have an operator which looks like this. AC is actually first companion form with a column A1, AN. So it is exactly this form. Here you have A1, A2, etc., AN instead of X, and you substitute it here. Well, I call the proof of this theorem a good exercise, because it goes like this. You take, you ask yourself, what is the condition for this theorem to hold, and you write this condition as a system of PDEs. You get 2n minus 2 system of PDEs, right? For companion form, you got n minus 1 system of PDEs, and here you have 2n minus 2, and you get the system which have two actually spatial variables, two space variables. One of you can call xn, the other you can call yn, and you get the system, and you need to check the compatibility. Everything is the same as in proof of first companion form, and the compatibility, it turns out, is exactly the compatibility is a vanishing of the following tensor, which is again follows, which is proved in the same lecture. Which means that in analytic category, we always talk about analytic category here. All the previous results were also in analytic category. This theorem holds. And it is a good exercise to prove it. So, any questions? Okay, that's it. Thank you very much.